Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the previous lectures, we have studied the topics which have laid down the theoretical basis of experimental model analysis. We also studied characteristics of FRFs, and we also looked at signal processing for model analysis. A bit of signal processing we will further study in later lectures. So in the next few lectures, now we are going to look at how experimental model analysis is carried out. We will look at what are measurements that are taken, how measurements are taken, and then how the measured data is analyzed to obtain the model parameters. But before that, we are going to today look at what is the basic principle of experimental model analysis. So the topic today is basic principle of experimental model analysis. And we will abbreviate experimental model analysis as EMA. So the first question is that what is experimental model analysis? So in one of the earlier lectures, we already defined what is experimental model analysis, but let us restate that definition. So what is EMA? So EMA is also known as model testing, and EMA is basically a procedure for experimentally identifying the natural frequency, mode shapes and damping factors of a structure or a system, right. So EMA is experimentally identifying the natural frequencies, mode shapes and damping factors, right, of a structure or a system. These characteristics, natural frequency, mode shape, damping factors, are also known as dynamic characteristics or modal parameters. So we can say that these characteristics are also known as dynamic characteristics of the structure or modal parameters, right. Now if we want to know these characteristics, can we measure them directly? Can we measure these characteristics directly? So can we measure modal parameters directly? Like for example, if we want to know the dimensions of an object, we can directly measure the dimensions of an object. So similarly, is it possible to directly measure these characteristics or the modal parameters? No, we cannot directly measure. The modal parameters, they depend on more fundamental properties of the structure, right, like dimensions, geometry, boundary conditions, material properties, right, and therefore they are related to these fundamental properties by an abstract relationship, like through an eigenvalue problem, and therefore they cannot be directly measured. Thus these characteristics cannot be measured directly. cannot be measured directly. Okay. So, how can we measure the model parameters? Or determine model parameters? Model parameters reveal themselves in the dynamic response of the structure to dynamic forces. Okay. So, therefore, if we have the knowledge of the dynamic forces acting on the structure and the response those forces result, then from these two pieces of information it should be possible in principle to determine the model parameters. Therefore, what can be done is that we can apply the forces on the structure and measure the forces being applied and the responses it results, right. And from these two pieces of information it should be possible to estimate or determine the model parameters. So, model parameters reveal themselves in the response to the dynamic forces. Okay. And therefore, knowledge of forces and resulting responses should in principle allow determination of model parameters. Okay. So, therefore, what is the basic principle of experimental model analysis? So, what is the basic principle of EMA? The experimental analysis can be performed either in the frequency domain or in the time domain. Okay. So, EMA can be performed in frequency domain or in time domain. So, let us look at the principle of EMA in the frequency domain first. So, in the frequency domain, the dynamic forces and the responses they cause, they are related by frequency response function matrix. Okay. And the frequency response function matrix essentially constitutes the response model of the system in the frequency domain. Okay. So, FRF matrix relates dynamic forces and responses in the frequency domain. Okay. So, therefore, FRF matrix constitutes response model, right, in the frequency domain. So, if you consider, let us say, a system with structural damping, right, then for a system with structural damping, if you look at, say, one of the FRF alpha j k omega. Okay. So, what is alpha j k omega? as we studied earlier, it is nothing but the response at jth degree of freedom to a unit amplitude harmonic force at kth degree of freedom, right. And for a system with structural damping, this relation we have the relationship between the frequency response function and the modal parameters that we have studied in one of the previous lectures, and that relationship is summation from r is equal to 1 to n if there are n modes of the system having n degree of freedom. So we have phi j r phi k r divided by omega r square minus omega square plus I eta r omega r square. So on the left hand side we have this frequency response function FRF, right, and on the right hand side what we have got is of course the excitation frequency omega, and apart from that we have the parameters like the jth and kth element, right, of rth mode shape, and then we have the natural frequency omega r of the rth mode, and then the loss factor of the rth mode. So these are the properties of rth mode, okay, and on the right hand side we have the sum from r is equal to 1 to n. So these parameters corresponding to all the n modes are present on the right hand side, okay, and of course as far as mode shape elements are concerned, they are corresponding to the jth and kth degree of freedom as we are looking at the FRF alpha jk. Now here the FRF, this can be obtained by measurement, can be obtained by measurement by performing a test on the structure, by where we apply the force and then measure the response, okay. And therefore this relationship tells us that the FRF are they related to modal parameters, and then by fitting this relationship to the measured frequency response function we can determine the modal parameters for all these modes, right, and of course the mode shape elements would be at the jth and kth degree of freedom. And if we have other FRFs also being measured, then the other elements of the mode shape also can be determined. So this is essentially the basic principle of the experimental analysis, right, that we basically measure FRF, okay, we measure the frequency response functions on this structure. So we basically then perform the fitting of these expressions to the measured FRF, which is referred as co-fitting. If we have a system, let us say with viscous damping, if we have a system with viscous damping, then we have the relationship between the FRF and the modal parameters given by alpha j k omega is equal to sum from r is equal to 1 to phi j r phi k r divided by I omega minus S r bar. So here also we see that on the right hand side we have the modal parameters of the system appearing, right, where S r bar is the complex eigenvalue containing information about the natural frequency and the damping factor of the rth mode, and then we have phi j r phi k r being the mode elements of the jth and kth elements of the mode shape, rth mode shape. So here also we see that we have the relationship between the frequency response function and the modal parameters, which then can be fitted to obtain the modal parameters of a viscously damped system. Let us now look at the principle of experimental analysis in the time domain. EMA in time domain. So in the time domain, the forces and the resulting responses, they are related by impulse response function matrix, right. So we have the IRF matrix, okay, and therefore this IRF matrix forms the response model of the system in the time domain. It is nothing but the response model in the time domain, okay. For a system with viscous damping, one of the IRFs can be written as HJKT, that is the IRF HJKT, which is nothing but the response at jth DOF when a unit impulse is applied at kth DOF. And for a system with viscous damping, this relationship for IRF HJK is given by sum from R is equal to 1 to 2n phi gr phi kr e to the power s r bar t, right. And here also we see that the IRF, this can be obtained by measurement, okay. So the left hand side of the equation can be obtained by measurement, and on the right hand side we have the modal parameters appearing in the expression. So we have the modal parameters. So if the IRF HJ can be obtained by measurement, right. For example, we can obtain that by inverse FFT of the frequency response function alpha JK, okay, and then we can fit this expression, this equation to that measured impulse response function, and then we can obtain the modal parameters in the time domain. So this basically forms the principle of experimental model analysis in the time domain. Therefore, the experimental model analysis essentially involves two major broad steps, right. So the major steps in experimental model analysis. What are the major steps? The first step is measurement of FRFs or IRFs. So that is the first step, and the second step is curve fitting of these FRFs or IRFs. Right. We can also represent this process by a block diagram. So we have excitation of the structure, and measurement of force and response, measurement of forces and responses. So that constitutes the first step. And what is the output of this activity? This basically gives us the FRFs and IRFs. And the next step is of curve fitting. And the output of this curve fitting is basically nothing but the modal parameters, right. And therefore, this whole process is basically referred as experimental model analysis or model testing. Now, how does the process of experimental model analysis compares with the process of analytical model analysis? Comparison of experimental model analysis and analytical model analysis, AMA. So, in the analytical model analysis, AMA, we basically have the spatial model of the structure, which is in the form of mass, stiffness and damping matrices, and then by the analysis of this model, okay, we obtain the modal model. So, we have the spatial model, okay, in the form of stiffness, mass and damping matrices, right, and then the analysis of this model through eigenvalue analysis, we obtained a modal model. In the experimental analysis, we basically have the response model of the structure, right, which is in the form of FRFs and IRFs. And then analysis of this response model basically leads to the description of the structure in terms of modal model. The modal parameters we obtain by analysis of the response model through AMA basically constitutes the modal model. So, therefore, we can say that the analytical model analysis is a forward route to identifying the modal model, right. We start from a mathematical model of the structure, and by forward analysis we obtain the modal model. But in experimental model we start from the response model, and then by an inverse procedure we obtain the modal model. So, in this lecture today we looked at the basic principle of experimental analysis, both in the frequency domain and in the time domain. I think we can now stop here. Thank you.